So I'm going to start this talk with a little bit of motivation and I'll explain. You can hear me, right? Yeah? Yes, good. Cool. I'll start this talk with some motivation and I'll explain what exactly it is I've done. So, a while ago, for my PhD, I was trying to work out what I should do, and I decided, let's write an interactive little editor simplifier for GHC external core. And this is kind of what I came up with. So we have this big yellow thing, which is where my cursor currently is, and I can move my cursor around. And when I move my cursor around, for example, there, I've highlighted one function, and that function is the only thing in scope. I'm going to say unfold definitions that are currently in scope of the cursor, and then unfold it down there, unfold the knob to the screen, and I think I can apply some detailed modifications as well. But what you'll notice is that all that's changing is the stuff that's in scope, and the stuff that's outside of the scope, or is outside of the focus, is staying still. So hopefully most of you have guessed that underlying this is some form of zipper design. But when I came to write this tool, I found that, yes, there's loads of literature on zippers, but it's not quite a good fit for what I was doing. And so I basically ended up writing this huge hack of horrible messy code to kind of get this structure to work. And then so I sat on it for a while, looked at it, and then decided, let's see if I can abstract this back and pull out a library. And so what I'm going to talk to you today about is a very small part of a library I've written that's based out of the experiences of writing that tool that should help make writing structured editors a bit easier. And it's called CLASE, for the very simple acronym. So there's a few code snippets in this little talk. Code that's in blue is code that a user will have to write, and so we've got a nice blue user. Code that is in the CLASE library is in green, so books are made from trees are green, libraries are made from books, so green library code. And code that is in orange is generated by some template Haskell scripts, and the best I could find is a picture of an orange being generated. So, I'm going to try very, very quickly to write structured editors using my library. I'm going to skip over a lot of it, but hopefully you should get the gist. So, here's the language we're going to use. It's a simple lambda calculus. We have a lam type that is going to be the root, so we have something that marks that we're at the top of our tree. We have expressions with abstractions, applications, and variables, and also because it's an editor, we might not have an expression yet, and we also have types. The point to prove here is that this data structure, or this library, works over languages that are heterogeneous. So we have expressions, and we have types, and we have lambs. So it's not all collapsed into one, it is separated. So very quick intuition about the CLASE cursor. Assume we have this kind of term. The idea is the focus is on the right-hand side of the application. So we have a current focus, which is obviously the term structure that's on the right-hand side of the application. And then we have a context. And the context is going to be a stack of constructors with holes in them. And these things are going to be auto-generated. So we have an application, the thing in orange is being auto-generated for us somehow. We have an application constructor that's missing one side of the application, and obviously that's where the current focus is supposed to stick into it. And then, so a cursor in CLASE looks like this. There's some stuff I'm not going to talk about. The point is the L is the type parameter for what the root of the language is, and that's, so in this case it's going to be lam. The A is the type of the current focus, and so the current focus is just literally a value of the current focus. And the context is a stack of, the context is a stack of this context type, starting from where you are, going all the way back up to the root. So we kind of have some type safety saying that you definitely can get back up to the root from where you are. So what are these contexts? Well, if I get the right link, this is the hand documentation for the library. Here's the cursor data structure as I've just described it. And if we have a look at the contexts are defined in this magical type class called language. And language is the core of this library. The idea is if you have an instance of this type class language, you can use CLASE to generate CLASE cursors, and then you can do useful zipper-like operations on them. So, for example, generically moving up, down, left, and right. So moving left, if you have an instance of the language type class and you have a cursor that's completely free variable there, you can then maybe move it to some other place. And because you might have moved it to some other place, we don't know what the current focus is, so it's accidentally quantified. And this is really useful in a practical sense, which I will hopefully get around to. So, that's a cursor. How do you get the instance of that type class language? So that when you saw there's a load of implemented functions there. Well, unsurprisingly, it's mostly boilerplate. And we've already had an introduction to template Haskell. Here I use it as a complete hack, just to get the internal structure of the data types and just spit it out to a file. So these are template Haskell splices with the dollars. The user has to write a bit of code to say, I want to generate this as the type class language, dump the type class language out into a module called lam language. The root of my language is going to be called lam, and the types that I want the cursor to be able to navigate over are lam's expressions and types. If you noticed earlier in the lam description, abstractions also have strings in them. I don't want the cursor to navigate over strings. All I want it to navigate over is lam's expressions and types. That's kind of a very useful practical distinction to make. And that generates a load of boilerplate code. Right, so one of the things that I found really hard when I was writing my little application is rendering. And this is rendering not the current subterm that's in focus, but actually rendering the subterm in focus and then highlighting it in yellow and showing the context around it as well. And the code that I did that in the original application was a mess. And I eventually kind of tried to abstract out the design pattern that I really wanted. So I kind of wrote what I would rather say, and then tried to make the rest of the library fit around that. And so what CLASE does is it also automatically generates for you a set of adapters. So here we have 4 adapters, one for the expressions constructors, one for the lam, one for the types, and one for the cursor. So the cursor is how you want to change the cursor to indicate that it's in focus, i.e. stick pointy arrows on it or highlight it in yellow. And the idea is that each of these functions will be called by a traversal, giving you the value of the constructor, but also calling the also passing it the results of doing a traversal on the traversable children of that constructor. So if you imagine when you're trying to render abstractions in this cursor structure, you have to render the normal abstraction value with x equals as whatever. But you also have a load of these constructors that have got holes in them, and so you have to explain how to render an abstraction there, and you also have to explain how to render an abstraction when you're currently focused, when the kind of focus is inside the expression and there's a hole there, or when the focus is currently inside a type and there's a hole there. And so this kind of type class helps with that. And so CLASE itself inside the library has a magical type class called Traversal, which is insanely complicated and uses far too many higher rank types. And then there's a nice function called complete traversal that has assumed you've got an instance of the type class, takes the cursor and gives you out a value. The boilerplate then automatically generates an instance of this traversal type class, so you can use the complete traversal function if you provide instances of all of the adapters, and something I can't talk about right now called bound, which lets you extract away binding information. And so, for example, to render the lam program the lam data type that I showed you earlier, this is pretty much all the code you need to write modular the definition of the monad that we're rendering over. So rendering an abstraction is a case of blocking out the name from the abstraction and giving names to the 2 arguments for calling traversal, the type and the expression, and then just outputting lambda name, has type, outputting the dot, and then rendering the expression. So what I can do at this point is show you some code, hopefully. So this is the complete code for this is the complete code for doing the rendering in this little example application we're doing. So we have our little render monad, which is reality of a mapping of variable indexes to names and also pointer for the output. Then kind of we have a code that I just showed you for the type class traversal instances. And then finally, the actual code to render, so to take a cursor that's defined for our lam language and turn it into a string. It's just a case of calling complete traversal and then a load of monad unpacking. And that also kind of infers enough information for GHC to work out which instance of the adapters and traversal we want to use. Right, so that's rendering. I've then used this library and use that rendering code to write a little UI. So this is how a user might write a UI using the thing. So here's some edited highlights of that. If you want to write a UI using this library, you're basically going to end up writing a loop with a load of callbacks if you're using something like GTK. And so it's great having a cursor that's parameterized by the type we're currently looking at. It's not very much good if you're in a callback loop, because obviously that type might change as you move from an expression into a type. And so we essentially wrap kind of a cursor in this little data holder, and then we can shove that inside some GUI state with a load of GTK variables and entities. When the user presses a key, what we want to do is move the cursor out, and so think of it as if you press H, what we're to try and do is move the cursor left, and if we can't move the cursor left, we'll move the cursor down. So the idea is you're always trying to move that way in the document when you press H, and if you press J, obviously you're going to try and move that way. So things to note here is those four functions are functions that are in the CLASE library. They take the cursor and they move it to some existentially quantified place. This move cursor function is one that we've had to write ourselves, and the definition of it takes as an argument a list of functions that move the cursor somewhere, and all it does is it unpacks the cursor from the IRF and gets an existentially quantified cursor because we don't know where it currently focused is. We then try moving the cursor using movement functions that are passed in as an argument, and if it succeeds, it takes the first one. If it does succeed, it then takes that out of the existential context, shoves it back into the existential context that we're using to hold it, and then writes it back to the IRF. That then gets passed off to Refresh-All. Refresh-All kind of redraws the cursor to the screen, and that just takes the structure, pull the cursor out of the IRF, rendering it using the render function, and then splatting it to a buffer. I don't have time for that, but it, of course, CLASE also includes a way of reflecting back to take a type that you're currently looking at and get back to the actual type that it currently is, and it does that by generating a little witness screen for you. So, very quickly, so I've everyone already. This is the entire source code for this little UI that I've written and trying to demonstrate to you. It's just under 400 lines of code, and about 200 of that is just in the GTK code, which goes on a bit. But here's the kind of function that lets you move about and also edit the cursor. And assuming I find the right place, so this source code is all available, so you can download it, you can extract it, you can move into it, you can generate boilerplate, hopefully you can compile it. Wow! Wasn't expecting that. So let's do get on. Good, fine. Yes, you can compile it, and then you can run it, and we get a little cursor pointing at the top left-hand corner of the screen. This is running, so I can press space, and I can create applications. I can press slash, I can create a lambda, I can give a name to that lambda, I can then go and refer to a variable inside there, I can wrap that up in another lambda, I can give that another variable, and I could change the variable to that, and etc. So, quick, simple, structured editor in about 400 lines of code. Yeah, I think it's useful. Right, there's a lot of other features that this library supports, so I've not been able to talk about. It lets you extract binding, so if you saw at the beginning of the definition, variables refer to the enclosing abstraction using the ground index, and all of that code is completely abstracted away neatly into one part of CLASE, and the rendering code never mentioned any of it, it just works. CLASE also so you can talk about part of the zipper tree and refer to a route going up and down to refer to another part of the zipper tree, and you can use that very easily to create bookmarks, and you can also persist the tree. Thank you for listening. I probably just spoke at 300 miles an hour, so you can actually download lots of information about this from the website. Thank you.